Yo, what is up, guys? Welcome back. Episode 84. Um, just gonna pump out a few more problems today. Gonna take a sip of this water. It's another good day to solve some problems. Let's take a look. Oh, we've got our Pokemon sound of the day. Let's check out episode 84. We got Pokemon 84. 83 was a Farfetch'd. We got 84 today, which is a Dodu. A classic. I like the evolution of this Pokemon. I don't remember what it is. I assume it's whatever 85 is. A Dod Trio. That's it. Yeah, bro. I used to love the Dod Trio. Dodu sound. Jeez. Oh, that was a trio. That's our sound of the day. We're gonna take a look at the life of a Dodu, because why not?
The Asado Desert, dry and barren.
Here's our Dodu.
Has
Let's
caught
go.
his attention. Perhaps a patch of greenery.
What is this, bro?
It looks like
Oh, the Dodu.
with
So cute.
potential threats deserve the victory cry.
There we go, man. There's our life of a Dodu. Now we can jump in and what does Leetcode Crash cost, dude? I'm good. $90, jeez. Nice, man. Cool, $90, dude. I will not be doing that. Alright. Let's take a look. Maximum value of an ordered triplet. Maybe we can take a look at our problem of the day. It is an easy problem, but we shall not be phased by it. Given a zero index array nums, return the maximum value over all the triplets of indices I, j, k, such that I is less than j is less than k. If all such triplets have a negative value, return 0. The value of a triplet of indices I, j, k is equal to nums I minus j times k. Okay. The value of the triplet 0, 2, 4 is equal to 77. Nums 0, 12. Minus nums 2, 1. So we got 12 here, times nums 4. 0, 1, 2, 3, 4. Nums 4 is 77. We've shown that there is no ordered triplets of indices with a value greater than 77. Isn't that 11? 7 times 7? 11. What do we get here again? We get 12. Okay. No, 11. Sorry, yeah. 12 minus 1 is 11. 11 times 7 is 77. Okay. It's 3 decibels. Okay, that's what I was thinking, but okay. I in range length nums. For J in range length nums. For K in range length nums. We all want to start at 0. We want to start at 1 here. We want to start at 2 here. Turn the maximum value over all the triplets of indices I, J, K, such that I is less than J is less than K. Turn the maximum value over all triplets of indices I, J, K, such that I is less than J is less than K. If all such triplets have a negative value, return 0. Num 0 minus 1. Negative 1 times 3. Hence the answer would be 0. And is equal to num 0 minus nums I minus nums j times nums k. If ands is less than 0, then ands is equal to 0. Ands is equal to 0. We want to find the maximum value, so let's do max val is equal to 0 here. We're going to find max val is equal to max val and guess we want to return our max val. Oh, forgot a. Oh, no, we don't need that. What am I doing wrong here? And negative value says 0. Let's print our answer here. -12 minus 1, 11. 11 times. Okay. I think we need to do. Why are we getting a negative value on these ones? 1 minus 2, 10. Minus 3 is 7. 7 times 19 is 133. $304. How the fuck do we get 304? How the fuck do we get? Negative 27. Or do 1 minus 10, 9, negative 27. Okay. I feel like we must be missing some values or something. Because then it would go, well, 110, then 4, which is 36. We go 110 and 19, which is negative 171. And we're done with that, so then we'd move 3 here, I think. 1 times 1 minus 3 is negative 2. Negative 2 times 3 is negative 6. Okay, maybe... Such that I is less than J is less than K. Okay. If I is less than J is less than K, then we run it. Okay. That's what we were missing. We'll basically submit. Consistency is key. See you tomorrow. Nice. Okay, we submitted it. But now, how can we make this faster? Of an ordered triplet 2873. Put in our root force solution. Give me hints to make this faster. First, traverse from the left to right and track max prefix I, max value before J. Second, traverse from right to left, max suffix K, max value after J. Then use a single pass over J to compute the result efficiently. Let's check out the Leetcode video.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem maximum value of an ordered triplet 1. And this problem is actually exactly the same as a different problem, but just take a look at the constraints for a second. So the length of this array could be up to 100, and the values could be, you know, up to 1 million, I think, between 1 and 1 million. But the length is what I want you to pay attention to, because this is the exact same problem problems, but hopefully this one is first and then the next one is right after that. But anyways, let's get into it. The main idea is pretty simple. We want to
So he just gives the brute force solution. Okay. Oh no, he's doing it 2 pass. He's computing the prefix sum, I think.
loops, pretty easy to do that. And then we calculate the value of the triplet. What we want to do is return the one that is maximal. So, okay, maximal. Now I'm thinking maybe this formula isn't a black box. Maybe there is some intuition we can get from this formula. But let's just start with the easy solution. Just going to be triple nested loops. So it's going to be pretty trivial to code that up. They tell us that the smallest value, the return value, can be 0. So if we only have negative values for all of our triplets, we would just return 0. So I'll initialize my result as that. And then I'm just going to go through the nested loops. I'm going to put the length type inside of here. We just want to maximize it. So pretty cookie cutter solution. Let's do our parentheses, nums of I minus nums of j multiplied by nums of k. And we start every pointer at 1 plus the previous one. So this way we will get every single possible triplet. We will return the one that is maximal. And so you can see, yes, this solution works, but there's actually a better one. And actually, there's an even better one from that as well. I'll cover the n squared solution. I think there's actually 2 ways to implement it, but I'll go ahead and cover one of the solutions. I'll cover the n squared solution, and now we're not going to think of this as a black box anymore. The word that I like to use is we're going to make some observations. So even though this is an easy problem, maybe you already know how to solve it, pay attention to the process that I'm following, because this sort of process is what you're going to want to do when you encounter more difficult problems that you have no idea how to solve. So now I'm taking a look at this. We want to maximize our result. So in this formula, if I wanted to take a shortcut or try to do some kind of like intuition to maximize this formula, what would I do? I'd probably want this number to be as big as possible, because that's going to maximize our result. Now, I don't want every one of these numbers to be as big as possible, because this number is actually being subtracted from this one. So actually, I want to maximize the number at index I. I want to minimize the number at index j, and this one is being multiplied by the result of that, so probably want to maximize this one as well. So now we kind of have a bit of intuition, and when I said shortcut earlier, that's another way of saying we're going to try to be a little bit greedy with this problem. If I had my 3 pointers, and let me kind of draw out some random example over here. So let's draw like a 2, 3, 4, and maybe a 2, and just some random values, whatever. Let's say I have my I pointer over here and my j over here. I take the difference between these, it turns out to be -1. Okay, then I move my j over here. Now the difference between these two is -2. And I'd keep going, and I'm not kind of drawing out the entire process, because even in a real interview, I mean, you're not going to have time to do a dry run with 3 nested loops. That's going to be very time consuming. So you got to take some mental shortcuts. So I'm thinking of this as, okay, I'm going to have my I pointer fixed here. It's the outer loop. I'm going to have my j pointer scanning through, and each time my j pointer is going to be out of position, it's going to be fixed as well, and then I'm going to have my k scan through the remaining portion. Okay, we're trying to pick the biggest value for the one at index I. What kind of shortcut could we take? Well, first of all, when I'm over here, my j value is bigger than over here. I could have my k iterate over the entire thing, but I don't think I want to waste my time doing that. I think when I see a value at index J that's bigger than the one at index I don't need to do that. I can just say, okay, well, screw it. I'm just going to take the shortcut and put my I pointer over here. And then maybe one more time. Now my J pointer's over here. Well, once again, this is bigger than that one, so I don't think I need to do anything here. I'm just going to put my I pointer over here once again. And the reason for that is not just because these two were negative, like the difference between those two was negative, but if we're trying to maximize the result, we want the value at index I to be as big as possible. Like if I have a choice to put my I value here or over here or over here, of course, I'm going to pick the biggest one that we've seen so far because it doesn't really matter. I could take the difference. I could subtract this from that or from that or from that. And the one that's going to be the biggest is always going to be the biggest number that we've seen so far. This is the greedy part of the algorithm. We take a shortcut and we say that the biggest number we've seen so far is always going to be the one at index I. And this idea alone is enough to take the n cubed time complexity and bring it down to be n squared. So in terms of coding, it's still a little bit tricky. Like, how would you translate this idea into code? And I'll tell you how I'm going to do it. It's a pretty standard thing. So we had like those triple nested loops, right? Like we had for I, and then we had for J, and then we had for K. What I'm going to do is eliminate this outer loop and only need these two, because I'm going to say, okay, this pointer is going to be the J value. This pointer is going to be the K value. It's going to tell me which value is going to be this one. And the reason I don't need this loop anymore is because we're being greedy. We're going to say whichever largest value we've seen so far with our J pointer is going to be the one that is the I value. We don't need to try every possibility. We only need to try the max that we've seen so far. Just to do a very quick dry run, because I know there might be some beginners kind of watching this. What I'm going to say is my prefix max, or I don't know what to call it. Maybe let's call it left, because we have a left, middle, and right. So I'm going to say my left is initially going to be the first value. Let's call it nums at index 0, which initially is going to be 2. And then I'm going to have my J pointer start at the second value, and I'm going to check, is this bigger than that one? Yes, it is. So all we do is just basically replace this with the new value, which is 3. Okay, now my J is going to be over here. Is this bigger? Yes, it is. So once again, replace it with the value here. It's 4 now. Okay, so now my J is over here. Finally, there is a...
Let's try and make this a little faster. Max val is equal to 0. Our left pointer is equal to num0. For J, J range like nums. Nums J is greater than left. Then left is equal to nums J. Okay. Then we have our like nums, and this always starts from I think J plus 1. Yeah. J. I feel like, would we break here? Go to our next loop. And here I think we do, well, nums I minus nums J. You go to left minus nums J. And then inside of here we do, well, ands times nums K. And then we'd want to do our max. We do the max of max val. Max val ends. We would just return our max val. I think. We have to think about the negative values too. Or is that values? J range like nums. We check well if J is greater than left. Left is equal to nums J. We break. Maybe we don't break. Do we break?
A smaller value over here. So now we kind of brute force the rest of this. We put K at the next spot. We know the difference between this and this is 2, so multiply 2 by 5, you get 10, and then K is going to be over here. Multiply 2 by 7, you get 14. Okay, that's the biggest we've seen so far. And then we once again continue. Now J is going to be over here. Once again, it's bigger than anything we've seen before, so go ahead and just replace the left value with 5. And now J is going to be over here, but now we don't have any elements for K, so we stop. And then I think the result we had was 14. The biggest product, I believe, would be this, and then 7. The biggest formula. So let's code this one up. So this was the code we started with. And I'm going to get rid of this loop, and then I can just shift tab these over. I can set my left value to the first one, and just cleaning up the code. This can start at index 1. This will start at J plus 1, and it will kind of continue.
Yeah, I did mess that up. We start from or if we had the break here. Nope.
You doing this. Now here, one thing we can say is if the value at J is actually bigger than the value at left, then replace it. Left will now be this value. Now we could put a continue statement here. I'm pretty sure it's not necessary. Putting a continue here would save us a little bit of time. It wouldn't change the overall time complexity, but it would save us some time. but I'm pretty sure it'll work without it anyway, because even though you might say, well, how can the left value and the middle value both be the same? You're right, they shouldn't be allowed to be the same. But at the same time, recognize that we're going to still take the difference between, that reminds me, over here, we shouldn't do nums of I, we should do the left value. Okay, good.
Left minus nums j. Left minus nums j times nums k. Max val is equal to max val and return max val. There we go. Okay, I don't know why mine went all the way up here, but
Good catch there. But recognize that the difference here is always going to be 0. So if you take 0 and multiply it by any value, it's going to be 0 anyway. So that's why you don't need a continue statement. Let me just run it to make sure. Yes, so you can see, yes, that this does work pretty efficient. Let's put a continue here, though. That should make it slightly more efficient. But there you go. You see it works. This is the n squared solution. Now, can you think of the actual linear time solution? It's also going to be a greedy one. I'll give you a hint, but probably tomorrow's daily problem will be that one, so you can also wait until tomorrow. But anyways, if you found this helpful, check out Leetcode.io for a lot more. Thanks for watching.
the greedy solution. How do we get the most max value, right? I feel like I maybe has to be the most max value in the array. No, that wouldn't work. The O of N solution. I don't know, bro. I was thinking, I feel like somehow we have to calculate our max value. Well, I has to be less than J.
Somehow we have to find. I feel like that's what it is. Somehow we have to find the 3 most maximum values here, right? Because
nums1 minus nums2 times nums4. Well, wouldn't it be nums1 minus nums3 times nums4? $30 times 19. Oh no, 10 because we're minusing. Yeah. Alright, so how we want to find the most maximum value? That's less than everything else. The most minimum value, that's less than everything else. And then the most maximum value, that's greater than everything else. That's because I had less than J. I was right. I was right. You need to iterate over the array, finding the most maximum I before J, the most maximum J, like the difference of I and J, and then the most maximum final result, which has to be greater than everything else. Do I want to implement that though? Yeah, fuck it, why not? Okay, so this would be our O of N solution. N solution. We'd want to find our max I, our max underscore J, our max underscore K, right? Our max I would be our most max value. That is, which I is less than J is less than K. Our max J would be our most max difference of nums I minus nums J. And then our max K would be our most max value. That is, that K is greater than everything else. But how do we implement this? Let's do for I in range, length, nums. Okay, we have to initialize our values, right? So we start at num 0. We'd start at nums 1, start at nums 2, right? So how we know our I? Well, I guess if nums I is greater than max I and
store a variable, we'll store the actual value. Would we need to store the indice?
I think we need to store the indice. We have 0, 1, and 2, so we check, well, is nums I greater than nums max I? And max underscore I is less than J and is less than K. Max underscore J and is less than max underscore K. Then we would make max I is equal to I. Then we check, well, if max underscore, if nums max underscore I minus nums max underscore J well, I guess if we have to make max I equal to I, then we would have to make max J equal to I plus 1, right? Because technically it always has to be ahead, or else we're going to get behind somehow, I feel. Max I minus max underscore J is greater than somehow need to store like a max J value or something is greater than max J, then max J is equal to nums max underscore I minus nums max underscore J. And finally, our last value, our K, we're looking for the most max value, right? So, if nums max underscore K nums I is greater than nums max underscore K, right? And K is greater than J and K is greater than I, then we make our nums, we make max underscore K is equal to I. And then here we'd want to, let's print our max underscore I, print our max underscore J, print our max underscore K. Let's just print a thing in, then we print our max J. Let's see what it gives us. This is probably horribly wrong, but K is not defined. What? And our max underscore K is greater than our max underscore J is greater than our max underscore I. But our difference here, which is 6. Our max value, which is 0. Max I, which is 0. So 12. Minus 6 is 6 times 6. 6 times 6 is 36. No.
though, but we were close. Damn, bro.
Xi is equal. Max underscore J, max underscore K. I'm 0. Okay, so apparently we need our float here. Right, okay. Now max K is obviously 0 for now. So we want to loop through. Right. To find our I, we want how much max value that is less than I but is less than J. So max underscore J is equal to the max of max underscore J and then nums I minus max underscore J. Sorry. Max underscore I minus nums J. Okay. Max underscore K. Then nums I. Max underscore K. Max underscore J times. Max underscore J times nums I plus 1. Sorry, nums J plus 1. Max I would be equal to the max of obviously max I, and then J minus 1. Nums J. Alright, okay. Num 0. Right, bro. Getting the maximum nums I minus nums J. Okay. And then we're getting our K by doing the max of that. Interesting. Definitely probably need to revisit it, but we'll kind of get into it. We've kind of spent a little bit long on this problem. Been nearly about an hour, so let's jump into a different problem. What do we want to do today? Let's check out our Leetcode 75 study plan. Take a look at this one. Reorder routes to make all paths is a device problem. There are n cities numbered from 0 to n-1 and n-1 road. But there's only one way to travel between two different cities. This network formed a tree. Last year, the Ministry of Transport decided to orientate the roads in one direction because they are too narrow. Roads are represented by connections, where connections I is equal to A. 0 to 1, 1 to 3, 2 to 3. Okay. This year, there will be a big event in the capital city, 0. 10 people want to travel to this city. The task consists of reorienting some roads that each city can visit city 0. The time the minimum number of edges change, it's guaranteed that each city can reach city 0 after the reorder. Oh, I just ripped ass. So I think this is similar to one of the other problems that we did where we reordered based on the edges, right? Because technically we look at, so 0 to 1, right? So the only way we get to 0 is through 4, right? So 0, 1, 2, 4, 4. So we have nowhere for 3 to go, right? So 3 has to go to 1, right?
Okay.
Traverse using normal DFS. Where we start the DFS from, index 0, right? Undirected, start DFS from the root. If you come across an edge in the forward direction, you need to reverse the edge. Okay. If we come across an edge in a forward direction, you want to reverse the edge. So we go here, that was the forward direction, reverse. We're going back. So no need. Forward direction, we would, that's okay. forward direction, we would reverse. How do we know? Trying to think. We did do our keys and rooms, or our numbers of provinces. Let me take a look at the code here. So it was and the number of cities. And cities number from 0 to n minus 1. Okay. Let's print out n. That's our cities, right? Oh, I could have looked down here, but whatever. Okay, we get our n cities. Okay. So, well, we want to make us visited. God, man, I'm gonna be a pro spelling visited, right? Visited is equal to set, right? These are the number of cities that we visited. It's tough for me to implement DFS using graphs. I'm a little confused on how to implement it. So we do visitors equal to set. City non-visited. Sorry, for city in range n. Just print out city. Just to visualize it, right? Yeah, bro, I'm a little confused. Six reorder routes to make all paths lead to the city 0. Lead to the city 0. Create an adjacency list. What is an adjacency list again? A representation of it. Traverse from city 0. Start at traversal city 0 using DFS or BFS for each neighbor city. Next. If next hasn't been visited, check if the original road current. If yes, we need to revise it. If no, it's correctly directed. We have our res, right? So step 1, we need to make an adjacency list. Okay, but how do we make an adjacency list? Okay, so we need to make some sort of list. Some sort of hash drive. Yeah. Is the empty list, right? I in range N. Let's print our adjacency list. I think this makes an 0 through 6 with empty values. Yep. Okay. 0 through 5. Yep. That's what I thought. Okay. So we need to go, well, for A and B in connections. Oh, sorry. Yeah, connections. Pretty much want to store B, right? So with A, badge A, dot append. Okay, so one represents outgoing edge. Edge B, dot append. A0. Which hashtag 0 represents incoming edge. A, so we started A, right? So our A, this case is 0. Alright. So then we're storing 1, which is where it's going to, with a value of 1, which means it's an outgoing edge, right? Otherwise, we're storing 1, which is where we're at, so at this point. And if it's incoming edge, we're storing 0. Okay, that's good. Let's print our adjacency list now. 1 1 4 0 0 0 3 1 3 1 0. Okay, all right. So now we start a traversal from city 0 using DFS or BFS. Okay. Okay, so let me think. We'd start
Started traverse from city 0 using VFS, CFS for serving city next. Next time,
How we restart the TFS though? Hmm.
My boyfriend and I have been arguing because he won't pay for YouTube Premium. But it's okay because I just downloaded AdBlock from Capital One Shopping. It blocks ads on my favorite sites, even YouTube and Amazon. I can surf the web faster without annoying pop-ups on my go-to sites, and I can keep earning shopping rewards. Just go to the Chrome store.
Let's solve Leetcode 1466, reorder routes to make all paths lead to the city 0. So this is obviously a graph problem. We're given n nodes or cities numbered from 0 to n-1, and we're given n-1 roads, which are the edges in this case. So the first thing to do is understand what the problem is telling us. So the problem tells us that there's only one way to travel between two cities. So basically what that means is that there's no loop inside of the graph. So for example, if I had 3 nodes, 1, 2, 3, I had one edge going this way, where can I put the second edge? Because we have 3 nodes, so we have to have 2 edges. Can I put the edge over here? No, because that violates the condition. Can I put the edge over here? No, because then that's a duplicate edge. So I have to put the edge over here, or put the edge over here. So the two things that this tells us about the graph is that there's no loops, first of all, right? So there's no loops in this graph. It also tells us that the graph is connected because we have n-1 edges. And if we can't put them, and if we can't create a loop with the edges, then that means we have to connect all of the nodes together. Once you can recognize this, the problem becomes a lot easier. This entities. So basically what that means is that there's no loop inside of the graph. So for example, if I had 3 nodes, 0. So this is obviously a graph problem. We're given n nodes or cities numbered from 0 to n-1, and we're given n-1 roads, which are the edges in this case. So the first thing to do is understand what the problem is telling us. So the problem tells us that there's only one way to travel between two cities. So basically what that means is that there's no loop inside of a graph. So for example, if I had 3 nodes, 1, 2, 3, I had one edge going this way, where can I put the second edge? Because we have 3 nodes, so we have to have 2 edges. Can I put the edge over here? No, because that violates the condition. Can I put the edge over here? No, because then that's a duplicate edge. So I have to put the edge over here, or put the edge over here. So the two things that this tells us about the graph is that there's no loops, first of all, right? So there's no loops in this graph. It also tells us that the graph is connected because we have n-1 edges. And if we can't put them, and if we can't create a loop with the edges, then that means we have to connect all of the nodes together. Once you can recognize this, the problem becomes a lot easier. So the next thing you want to do is draw a picture because that makes it a lot easier for you to visualize it. I've already done that over here, so let's start looking at the problem. So we want every node to be able to reach 0. So the first logical thing to do is look at 0, right? Oh, and just look at its neighbors, right? Let's first see if its neighbors can at least reach 0. Let's first look at 4. 4 can obviously reach 0. We have a direct edge going from 4 to 0, so we don't have to do anything there. But what about 1? There's only one edge between them, and that edge is going from 0 to 1. So we have to change this node, right? We have to go back to 0 from 1. So now we at least know that all of the neighbors of 0 can reach 0, right? So we've checked 1 and we've checked 4. But what about all of the neighbors of 4, for example, right? Can all of 4's neighbors reach 4? Because if we know all of 4's neighbors can reach 4, then all of those neighbors can reach 0 because we know 4 can reach 0. So let's check if 4's neighbors can reach it. It only has one neighbor, 5, and 5 can't reach 4. So we also have to change this edge. now we know that 5 can reach 4 and 4 can reach 0, so these nodes can reach 0. What about 5's neighbors? Well, it doesn't have any. So now let's go back to 1. We know 1 can reach 0, but can 1's neighbors reach 0? It has one neighbor, 3, and it looks like the edge is going from 1 to 3, so we have to change this edge as well. So now we know that 1 can reach 0 and 3 can reach 1, so therefore 3 can also reach 0. But what about 3's neighbors? Can they reach 3? 3 only has one neighbor, 2, and 2 can reach 3, so we don't have to change any edges. But what about all of 2's neighbors? 2 doesn't have any neighbors, so we don't have any more nodes to visit. Now we've determined that every node can reach 0. We did this sort of recursively or propagating changes, right? First we wanted to check, starting at 0, can 0's neighbors reach 0? Okay, if 0's neighbors can reach it, can their neighbors reach it? That next layer we're checking, right? We're checking 3 and 5. And then if those nodes can also reach 0, can their neighbors reach 0? We check the next layer and there's only one node there, only 2, right? So it's kind of like a breadth first search. We're just propagating outward to change all outgoing edges, right? We want every edge to be pointing back in the direction of 0. With this traversal, we only have to visit each node once, so we can say that the time complexity of this is big O of n. So now let's get to the code. Before I start, I like to write some comments just to remind myself what to do. So remember, we're going to start at city 0, and we're going to recursively check its neighbors. And we're going to check that the edges are, if the edges are outgoing, we're going to count them. We don't actually have to change them in this problem. That's not a requirement. We just have to check the number of outgoing edges that exist. So this problem gives us a list of connections, but we want to instantly be able to check if node A or city A can reach city B instantly, right? So let's make a set to do that instead of an array, right? I'm going to use set comprehension in Python to do that, so I'm basically getting each connection, adding it to a hash set. Next, we want to know each node's neighbors, not if we can reach that node itself. We want to know any adjacent neighbors of a node. So we're going to use a hash map for that. Again, we're going to use comprehension to do that, so dictionary comprehension. For each city, we're going to have an empty list initially. We also only want to visit each node once so that we have the most optimal solution. So we're going to use a hash set to keep track of visited nodes. Also, we just want to count the number of edges that we have to change, so we'll just use an integer to do that. Next, we're going to fill up our neighbor's hash map. So in this case, the neighbors of A includes city B, and the neighbors of city B include city A. Now we want to write our function to actually traverse the graph. You can do this a bunch of ways, iteratively, recursively, depth first search, breadth first search, but I'm going to do this depth first search recursively. To make it most convenient, I'm going to use non-local variables so I don't have to pass them into every function call. So for each city, we want to iterate through each of its neighbors, right? So we can do that pretty easily. If the neighbor itself has already been visited, we don't want to traverse it again, so we'll just continue to the next iteration, to the next neighbor. So next we want to check if this neighbor can reach city 0. So the way we can check if this neighbor can reach city 0 is simply by checking if the tuple neighbor city exists in our set edges. If it exists, that means neighbor can directly reach the city that we're currently at. If it's not in this set, that means that the edge is outward, so we have to change this edge, so we have to increment our count. Once we visit a neighbor, of course we have to mark that it's been visited, so we don't visit it again. Lastly, we have to recursively run depth first search on this node, because we know that this neighbor can now reach city 0, but we want to check that this neighbor's neighbors can also reach city 0. We're basically propagating the changes. Lastly, we want to actually run our depth first search function on city 0, of course, because that's our starting point. But we also have to remember that we have to add this city as well to our set to mark that it's been visited. Lastly, all we have to do is return the total number of changes that we made. We don't actually have to make the changes themselves. Oops, I had a couple typos. I used the plural of neighbors instead of neighbor. You want to make sure that you don't have typos like me. And then let's resubmit it and make sure it works this time. Yep, beautifully. So these are the steps you can take. Our time complexity was big O of n.
Damn, bro. This is tough for me to think about, man. Really? Well, technically we've done all this, right? Cross problems are tough, man. Very tough. Like, Because apparently we use visited.add city. They use just a normal array for neighbors and needs. Man, this is really tough for me to think about. Like, really, really tough. I'm gonna do the BFS example because I feel like thinking about it iteratively may help. Right, so passing 0, right? We want to add 0 to our visited set is equal to set. Oops, set 0. Oh, dude, oh my gosh. Right. While we have something in our queue, we want to pop, right? So let's say, what? Yeah, city is equal to queue dot pop left, right? For neighbor, it needs reversals. If neighbor not in visit, visit.add neighbor, q.append neighbor, reversals plus equal to needs reversal. If neighbor not in visit, visited.add neighbor q.append neighbor and reversals plus or equal to these reversals. Reversals. Oh, we don't have reversals. Whoops. Okay. Let's print city. City 0. So we're looking at the neighbors. So I think it's the neighbors that move off, right? So let's print our so what we do here is you print city. So we started 0, right? Print the city for neighbor and needs reversal on adjacent city. Our first one goes to 1, right? Okay. 1 1. Then we go from 4 to 0. Man, this stuff is tough. I'm trying to learn, bro. This shit is not working. Man, Jesus. Zeros visited. Name is 1 1 and 4 0. Oh, okay, plus equal to needs reversal. Needs reversal is always 1. Okay, I understand. Okay, that's very smart. I didn't think about that. Okay, initialize. We started 0. We see the neighbor 1. Needs reversal 1. Visited 0 1. Reversals 1. We have 4 0. 0 is correct, so we visited 0 1 and 4. Okay. Then we go to our next iteration, which would be the 1 1 run that we passed in. One 4 0 already visited, so we don't need to do it. 3 1 reverse 0 1 4 3. Nice. And we have 4 3, so we go to our next element 4, and we see, well, in 4 we got 0 1 and 5 1. So 0 1 we already visited. We haven't visited 5, so we reverse 5. And we have 3 0 3 is already visited. So it's already visited 2 0. 2 0 is correct. We reverse 3. This shit is pissing me off, dude. Oh my god, dude. Seriously, bro. Man, this is tough, bro. This is tough. Tough stuff. I had to do the stack. I mean, it's pretty much the same thing, right? We do stack is equal to... Right? I'll stack. Up. And I think it's pretty much all the same, bro. Like, remove stack. Like, yeah, bro. So stack. Come back to it. We got a stack solution. All right. And we got a queue solution. Let's submit that to... left. Yeah, I have a feeling, low key, I do actually like tree problems, and I really feel like I'm gonna like graph problems too, because I like implementing BFS DFS, but I just feel like I have to learn how to implement it properly, because obviously right now I can't really think about it in the way that I want to, but once I can do that, after I do keep doing problems, then, you know, I think eventually I'll feel confident, you know, with it in a way. Let's take a look at Leetcode's roadmap for graphs. We'll take a look at the number of islands. I think this is a classic problem. I think we did this one actually. Maybe it's in Leetcode 75. I think it is. Q. No. Number of islands. Created represents a map of 1's land and 0's water. Return the number of islands. The island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are all surrounded by water. Okay, right, so an island would be like... Oh, okay. You could have multiple islands, right? So I feel like... Well, this would be one island, right? Because you have 1, 1, 1, 1, 1, 1, 1. They're all connected. Therefore, this is a BFS or a DFS problem. Okay. Definitely an interesting way to think about this problem. I feel like it is similar to the rotting oranges problem, but still different. Definitely is similar. Nearly been going 2 hours. These graph problems are tough right now, man. Okay. So really, like, let's think about how can we kind of solve this problem, right? So we have each island. Okay. Do we somehow want to count each of the 1s and 0s? I don't know. Numbers of islands. Oh, my mic's messed up. Sorry, guys. Nope. Okay. I think that fixed it. Okay. Okay, we want to traverse the entire grid, right? We need to get our rows, so our rows would be the length of grid, right? And our columns would be the length of the first element in the grid, right? So let's print our rows, and we'll print our columns. Oh. What is going on here, dude? Non-type is not a valid expected return type integer. Dude, I'm not returning anything. Just printing out rows and columns. What the hell? What is going on here, dude? Return rows. Okay, alright. Whatever, we'll just keep that. Print rows. Let's print out columns. Okay, so we got 4 rows. 1, 2, 3, 4. One, two, three, 4, and our columns are 1, 2, 3, 4, 5. Okay. Island is equal to 0, so we'll return our islands. Right. Now I want to think about, well, how do we want to loop through this? Okay. For R in rows, in range rows. For C in range columns. Okay, so if grid RC is equal to 1, right? We need some sort of like visited set, I think. Visited is equal to 0. And we need some sort of, I think, Q from collections. Import DQ. RC is equal to 1. And grid R C not in visited. Visited, we need our set. We want to put in grid 0, 0, right? Because we start there. Whoops, grid 0, 0. We need our Q is equal to DQ, grid 0, 0. Okay. Let's print out visited. Expected an indent. Okay, let's get rid of this. Oh my gosh, dude. I just want to visualize this. We have 1. We don't want to hold the actual value. We want to hold we want to hold the tuple. I think that's probably what we want to hold. We want to hold the tuple, right? Zero. Track the coordinates here, not the actual. All right, RC. Okay, we don't need this then. Okay. We need our directions though. Tons are rows are calls. Our directions are visited. Not our queue. Get rid of the print. I need our directions set. Directions is equal to, well, -1 0. -1 0. 0 -1. Okay, right, so we loop through for R in range rows, for C in range calls. We check, well, if grid R C is equal to 1. And RC not in visited, then we want to call our DFS. We call our DFS function, so we call DFS RC. And our islands plus or equal to 1. Right, we want to return our islands function, right? We want to call our DFS function, passing in our rows and columns. Okay. So the first thing we want to do, well, we probably want to initialize our queue, our stack, right? So our stack is equal to, well, RC, I would assume, right? Yeah. And then we add to our visitor array. Visitor is equal to visited.add RC. Okay. And we have, well, while our stack has something in it, we want to pop, right? So we'll call island is equal to island.pop. Okay, we're popping. We don't want to pop our island, we want to pop our row island and our row col, sorry, our col island is equal to stack.pop. For row island, col island, in in directions. We want to check each direction, so we want to do, well, I just want to do, well, our new row island is equal to x plus our original row island, and our new col island is equal to y plus row island, right? Yeah. After that, we want to check, well, if 0, same as rotten oranges, if 0 is less than or equal to new row island, which is less than the length of, we could put rows, right? Our original rows, which holds the length of the grid. And 0 is less than new col island, which is less than cols. Well, we technically 0 is in bounds, so we can make it equal to 0. And grid new row island new row col is equal to 1, then this would be a new island, right? So we would q.append our new row, our n row island and our n coal island. We'd also mark it as visited to, so visitor.add new row island, new coal island. We have to check if it's in visited too, I think, right? Yeah. And new row island, new row, new coal island, not in visited. Then we can simply append and also increase our islands by 1, I believe. Islands plus equal to 1. Sorry, we don't have a queue, we have a stack. Oh, wait, no, we're not increasing our islands, right? Because this is one island right here in the loop, right? This would be one island. So we'd add to our stack, and then we'd add to our visited too. We would just return our islands. I believe this hopefully should run. Visited is not defined. Jesus, man, I always spell it wrong. Visited. We need a double parenthesis. Access local variable DFS. I think our DFS function has to be above. I think it has to be above, maybe. And row call. Oh, sorry. New coal island. I knew I was going to spell something wrong, bro. Is our directions correct? -1 1 0 0 -1 0 1. Okay, it is. Are we adding our statement correctly? 0 is less than new row island is less than coals, and 0 is less than or equal to new coal island. And grid and row island and coals equal to 1. And I'm not sure what's wrong here. Small issue how you're updating the coordinates. Oh, whoops. There's our problem right there. I knew it was something small. Oh. Oh, it's because I'm adding row here. You want coal. There we go. Okay. finish that problem. I think it was good thinking today. We're going to keep going with graph problems, keep learning, really trying to understand the patterns. And, yeah, we'll be back tomorrow. Appreciate you guys watching.